All right, welcome to chapter whatever that we're on. I don't actually know. Somebody has got on the chat here and said audio's good on Zoom, which I'm delighted to hear. All right, so supercomputing in plain English, high throughput computing. So all the usual disclaimers with one extra one, which is that unfortunately the room we're normally in, another meeting got scheduled into and they were there first. And there were a lot of them, so I didn't feel like I could just throw them out. We're in a different room. You can find the room. Make sure you do all this good stuff and things and stuff and the usual things and the stuff and the things. Yay. Okay. And questions to supercomputing in plain English at Gmail as usual. Right. So we've got 3 more sessions this week, next week, and the first day of May, May Day, our last 3 sessions. So we're sliding into home plate here. We're doing really good. Thanks to everyone for helping. You coming up. Oh, and tomorrow is the cadre conference at Oklahoma State. So I'm driving up tonight for their reception, and then tomorrow for the actual event. So it's going to be very exciting. Okay, so high throughput computing, we'll talk about what it is, tightly versus loosely coupled, opportunistic computing, Condor or HT Condor as it's now known, and grid computing, which will lead into a little bit of a discussion about cloud computing as well. So high throughput computing is qualitatively different from high performance computing in the sense that we may not necessarily care how long it takes for an individual job to run, and we may not care about how many calculations it's doing per second. We're much more interested in how many jobs it can do per day or week or month or year. That's a much different kind of measure from performance, which we usually measure in calculations per second. So we're not trying to get a specific job done quickly. We're trying to get many, many jobs done as quickly as possible. Okay, and I think we're being joined by the thing there. All right, good. Okay, so throughput, a good way to think of throughput is from the time you submit a bunch of jobs until the time that all of those jobs have finished. Whereas performance, we're really thinking about how much the time the job takes from the time it starts running to the time it ends running. And we usually think of performance in the context of once it started, it doesn't stop. Whereas throughput, it might start and stop and start and stop. So for example, if I've got a very big job and I submit it on January 1st at 1 a.m. and then it sits for a long time in the queue, and eventually the next morning or the next evening it starts running, and it finishes running an hour later, then the performance is lovely, right? I got the job done in an hour. But the throughput is terrible. It took me a day and a half, right? So that's maybe a good way to think about the distinction between throughput versus performance. Now, can you get high throughput on a cluster supercomputer? Yeah, you can, as long as nobody else is trying to use the cluster supercomputer. If you've got $1 million and you buy one for yourself, you can get all the throughput you want out of it. But if you're going to be sharing it with lots and lots of other people, which is usually the case, usually there are hundreds of other users, not all day, every day, but over time. There are many hundreds of other people, and they're keeping it loaded up with jobs all the time. Then, you have to pick the right time to submit the jobs. And, if you get lucky that today it's less busy in a particular way than on other days, then you might get your jobs to go through the machine. It's a lot of different factors that are going to control how long it's going to take to get your work done. And most of those factors have nothing to do with you, and you can't do anything about them. Right? Okay, so now we're going to recap a little bit. This is from 2 lectures, which is like 3 or 4 weeks ago. We talked about the distinction between tightly coupled versus loosely coupled applications. So a tightly coupled application is an application where the many different things that are happening all have to happen together in lockstep. And weather forecasting is a beautiful example of this. So when you're doing a weather forecast, if you're doing a forecast over this part of the US, so centered around Oklahoma, then the weather on the border between Oklahoma and Kansas, the northern tip of Oklahoma had better match the southern tip of Kansas. And in particular, they'd better be at the same simulated moment, because the different processors that have the different chunks of Oklahoma and Kansas, if they're at different times of day, then as the storms typically are moving from southwest to northeast, as the storm is crossing the state line between Oklahoma and Kansas, you're going to have a big problem if one of them is at 1 o'clock in the morning and the other one is at lunchtime, right? Because the storm is going to try and cross from one state to the other, and suddenly it's going to leap forward in time half a day. That's not going to work, right? So what you have to have is they have to be synchronized to, in a typical case like this, to the second, or if it's going to be a molecular dynamics simulation, perhaps to the femtosecond of simulated time, right? Not real life time. But they have to be at the same simulated moment, because if they are at different simulated moments, then the relationships between the parts will not make any sense, right? And so you get nothing but wrong answers. Remember, good rule of thumb, it doesn't help to get the wrong answer faster. The goal is to get the right answer. If you can get the right answer fast, that's even better. Okay, so tightly coupled applications, it's very, very important. Everything, all of the different pieces that are solving the problem, they have to be advancing forward in lockstep. There's very little room to maneuver there. So they're constantly synchronizing with each other. Everybody is, for example, doing a bunch of number crunching, and then everybody is exchanging data. Everybody's communicating. And then everybody does some number crunching, and then everybody communicates. And then everybody does some, and from time to time, you're going to write some data to disk, and everybody's going to write data to disk at the same moment. Otherwise, it's hard to interpret what's in that file of output if parts of that file of output are at this time of day and parts of the file of output are at that time of day, and then there's another part that's at this other time of day. It's really hard to interpret what that file of output means. So you want all of the parts to match up and have the file represent one moment in time, right? So the file represents midnight or 1 a.m. or 2 a.m. or whatever it may be, right? It's very, very important that all of that is happening in lockstep. Whereas in a loosely coupled application, you can have the many different things happening at the same time, but oftentimes you don't care at all where they are in the calculation. Or if you do, you only care about that from time to time. It's not a constant worry the way it is in a tightly coupled application. In a tightly coupled application, every part of it has to be in lockstep with every other part. I mean, there's maybe a little room to wiggle on that, but frequently everything is synchronizing so that even if they get a little bit off of being perfectly synchronized, they resynchronize frequently. And so they're more or less in lockstep, even if they're not perfectly in lockstep. Whereas in a loosely coupled application, all the different tasks could be at totally different places in the calculation, and it doesn't matter. Maybe once in a great while, there's some kind of synchronization, but not very often. Okay. So, and I was just talking about the weather forecasting. So here's a picture of that, right? So this is actually more or less the border between Oklahoma down here and Kansas up here. It's hard to see because the lines are very thin, but that thick black line is the boundary between here's Oklahoma and here's Kansas. The thick black line is the boundary between them, and they have to be, depending on the resolution of the forecast, let's say they are a second or less different in time. They're all happening at the same simulated moment, and they're constantly resynchronizing to make sure that that remains the case. Because otherwise, that storm that's traveling from Oklahoma into Kansas, when it hits the Kansas state line, all of a sudden it goes from midnight to lunchtime. And that's no good, right? You've missed all of that physics between midnight and lunchtime. Not a good thing. Okay. So we talked a couple of weeks ago, 3 weeks ago, recently, we talked about embarrassingly parallel problems. And the embarrassingly parallel problems are the ultimate version of loosely coupled. So if there's no communication at all among the various pieces, so they never have to synchronize, then that's as loosely coupled can possibly be. Sometimes you need a little bit of synchronization once in a while, so they're not perfectly loosely coupled, but they're largely loosely coupled, and that's not a bad thing, okay? But the idea is that the more loosely coupled, the easier it is, for example, to run those pieces completely independently of each other. So I'll give a concrete example of that. I talked about Monte Carlo methods where we generate a finite number of randomly generated realizations of a particular physical situation, and we calculate the properties of each of those to get an average that is roughly the average of the infinitely many cases that exist in real life. Okay. We cannot, of course, run infinitely many cases. We can run finitely many cases, and either we know how many such cases we need to run to get the statistically correct answer to within the tolerance that we want, or we just add more and more cases until adding more and more cases does not get us a meaningfully different answer to within whatever tolerance we want. We call that convergence. When the many cases converge to some answer, we figure that answer is probably the correct answer. I'm not going to get into all of the math underlying that, let alone all of the actual science underlying that, because that's way beyond my level of understanding. I only understand the computing parts, but that's roughly how these things behave. Okay, so the example that we looked at a few weeks ago was high energy physics, banging tiny particles together at unbelievably high speed. And so the way that they do this in real life is they do two things. One is they bang tiny particles together at unbelievably high speed in the real world. And so CERN, and I used to know what that stood for, but I've already forgotten. And also I think what it stands for is in French, not English. But anyway, CERN, which is the big lab in Switzerland, although bits of its accelerator are in other countries nearby. I think part of the actual track that the particles go on is in France, maybe in Italy, something like that. Anyway, CERN, the Large Hadron Collider there, they are colliding particles together, banging them together at unbelievably high speed. And every time they do that, they produce a zillion gigabytes of data. In fact, they produce so much data that they throw away something like 99% of the data they produce immediately, right? Then they take the remaining, I don't know, 1% or thereabouts, and they farm it out to, I'm not making this up, 150 different countries around the world. So 3/4 of the countries in the world participate in this project. And all of them, they have various computers doing stuff, and those computers are reading this data that's coming from CERN, and then they're figuring out, they're looking for the patterns that indicate whatever the heck it is that they're looking for that I don't understand what it is, but what was it? The Higgs boson? So you actually probably know way more about that coming from a physics background. You probably know more about that. I know nothing at all about what it means, but it sounds really good. And they announced they found it a couple of years ago because of these kinds of experiments. Now, the other thing that they do is they do a zillion simulations of banging tiny particles together. And the reason that they do a zillion simulations of that is because they want to make sure that the equations of the physics that they think govern banging tiny particles together actually resembles the reality of the data they collect. And so there's a ton of these calculations, and of course there are infinitely many ways to bang two tiny particles together. So what they do is they generate a zillion randomly generated realizations of banging tiny particles together, and they look at the statistical properties of those, and they compare those statistical properties to what they find in the data. I've massively oversimplified this, and also I don't know what I'm talking about. So between those two things, you've gotten a very simplified version of the reality, but that should roughly capture what's going on. And those zillion realizations that they generate are all pretty much independent of one another. And so they run, not every single realization runs as a completely independent job. Typically, a job will package up a small number of these realizations, I think tens or hundreds of them, and will run for some reasonable period of time, like 24 hours or whatever it is. But roughly speaking, every job is independent of every other job. Every realization, every randomly generated simulated banging tiny particles together is completely independent of all the others, and they know how many they need to generate, which is essentially they're just going to keep going. And then they're calculating some, I don't know what, based on what they're getting out of that to make sure that those look like real life. Okay, so that was a long-winded explanation, but captures the idea of all of these things are independent of one another, and they have a zillion of them to do. So rather than try and run them in lockstep, which would be very, very hard, they can all run independently of one another. So that's a good thing. All right, I already said all of this. Blah, 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 blah. Said all that, embarrassingly parallel, right? Break it up into chunks, hand a chunk to each of the processors on many, many machines all around the world, and they do magic. Okay, and then I had shown you last time sort of this would be the way to do it if you were trying to run it all inside one program running just as one big thing, which would take forever and you couldn't build a big enough machine for it. But you can parallelize that, and I kind of show an MPI version, but you don't have to do MPI at all. You can just run a zillion of this and get just as good an answer much more straightforwardly. So really what you do here is you just change the input and say run fewer of these, but then you have many such runs. Okay. In fact, one of the interesting things for a Monte Carlo simulation is not how do we generate the zillions of cases. It's how do we make sure that our numbers, that our random numbers are actually random. That's actually a much more interesting and difficult problem, having really random numbers, because, and I'm not going to spend all day on this, but it turns out that our random number generators are not random and therefore are not generating random numbers. They are pseudo-random, which means they are generating pseudo-random numbers, which are numbers that are not random, but behave a lot like random numbers. And if your head has not exploded yet, I'm sure I can make it worse. So there are mathematicians who study how to simulate random numbers using numbers that are not random, and how to do that in a way that's really good for simulations where you have many parallel cases. And there's lots and lots of literature about this, none of which I know how to read. Okay, so having gone through that monstrosity to get to this point, the idea is we've got zillions and zillions of tasks to do in these loosely coupled problems. Well, if we've got zillions of tasks to do in a loosely coupled problem, we need to have lots and lots of computing. And sometimes the problem is we can't afford that. So let's talk about something else called opportunistic computing. So now the computer I have right here is a laptop, which means when I'm not using it, I close the lid and then it's off. And so nobody else can use it either when I'm not using it. Mine actually has a password on it, unlike my wife's over here, which you just click the sign in button without knowing her password and suddenly you're logged into her computer. I don't do that. I have a little password on mine. But anyway, so nobody can get in and use my computer when I'm not using it. It's only running when I'm using it, okay? But if I had a desktop PC, and I up until recently did have a desktop PC as well as the laptop, well, the desktop PC doesn't shut itself down when I'm not logged in. It's still sitting there. It's live. So if you think about a bunch of PCs, let's say at OU, at this institution, we have, I think it's reasonable to guess, we have probably several thousand PCs. Some of them are in PC labs. Some of them are on the desktops of various staff members or faculty or students. And I'm willing to bet that a significant fraction of those folks, and by a significant fraction, I mean approximately all of them, do not shut down their desktop PC when they leave for the day. Just out of curiosity, I'll take a quick poll in the room. How many of you, when you leave for the day, you physically power down your desktop? Okay, one person in the room actually does that and nobody else. All right, so, yeah, well, that's what the laptop is for, right? Okay, so you're leaving it on all night anyway, right? You worked on it for 8 or 12 hours, however many hours you work, but it's active during the daytime, during business hours, but then you go home at night, right? So while it's sitting there at night, you could be using it to do something. You just don't happen to be. If you used it to do something, you could double or more the amount of value you were getting out of it, right? And you've already paid for it, right? It's a fixed I think the economists call this a sunk cost. You've already paid for it. It's too late to change the amount of money you're going to spend on it. So if you could get more value out of it, that'd be a win, right? So if you think about, for example, a PC lab, and there's several of those here on campus, and I think most academic institutions have labs all over campus with PCs in them. And our PC labs here at OU, I think most of them are open 24/7, 365, right? If you want to go in at 3 in the morning on Christmas Eve, nobody will stop you, right? You got to have swipe access to the various labs. Not every lab is open that way, but so for example, I'm in engineering, and there's some engineering labs, and I've got card swipe access with my OU ID card that I can swipe a little swipe reader, and there'll be a click, and I can walk into that lab at 3 o'clock in the morning on Christmas Eve. I'm not going to, but I could, okay? So if those labs, the PCs are turned on, they're sitting there idle, if only we could get more value out of them, right? They're sitting there idle anyway. So this idea that came about, several decades ago was, what if we had opportunistic computing when the thing is sitting idle, and we'll define that as the CPU load on it is low and nobody's touching the keyboard or mouse. If the CPU load is low and nobody's touching the keyboard or mouse, we assume that it's being not used. If it's being not used, somebody else could use it, okay? So this is called opportunistic computing. I notice that it's not being used, so I'll start using it. Okay, well, what does that mean? Well, one of the ways that this has manifested itself is through external projects that need computing. And one of the most famous is SETI, the Search for Extraterrestrial Intelligence. Now, the goal of SETI is to find the green bug-eyed monsters out in space. Now, clearly, these folks have not seen the movies I've seen, because in all the movies I've seen, when they find out about us, their first goal is to come here and eat us. But leaving that aside, the green bug-eyed monsters out in space, if we could find them, that'd be like a big, big science win. We'll leave aside all the other questions. I'm sure you've seen plenty of science fiction movies too. We'll leave out all the other questions, but if we could find them, it'd be a big win for science. Oh, look, there are green bug-eyed monsters out there. Okay. So the SETI people wanted to find that, and the way they have for looking at that is to look at gigantic piles of radio astronomy data, okay? There's tons of this data out there, and there may be signals in the radio astronomy data that will tell us, that will indicate to us that there are indeed intelligent green bug-eyed monsters somewhere out there who are listening and maybe even trying to communicate with us in some way. Okay? So what the SETI folks did was they had this brilliant insight. They said, okay, so there's no way that the US Congress is going to give us the many millions and millions of dollars that we're going to need to have enough computing capacity to find the radio astronomy signals that will show that there are green bug-eyed monsters out there trying to talk to us, or perhaps to each other, okay? So since no one will give us a big grant of millions and millions of dollars to search for green bug-eyed monsters out there, then we need some other way of getting our hands on a huge amount of computing. So this brilliant idea was, let's have a screensaver, a thing that runs when your computer is idle, like the screensaver does, except what it'll do is it'll go to some central place, it'll download some radio astronomy data, and it'll start chewing through the radio astronomy data. And every so often, it'll send sort of the results of its analysis back to that central place and say, nope, no green bug-eyed monsters in this data, and then download another chunk and do that. But it'll only do it when there's nothing going on of significance on the computer and nobody's tapping on the keyboard and nobody's touching the mouse, right? Only when it's in screensaver mode, okay? So that's fair. Okay. So they set up SETI at home, and there are now tons of other projects of a similar flavor. So there's Rosetta at home, which is trying to cure various diseases. There's Einstein at home, which is the LIGO thingy. I don't know what any of these things really mean, but there's a zillion of these, right? They're looking for various prime numbers. They're doing climate predictions, a whole bunch of these projects out there. And they run on top of a software infrastructure that is in some ways similar in look and feel to MPI, although it's less focused on sending messages among various PCs, more focused on opening files and reading them and then opening other files and writing them, where the way. So really opening a file means downloading it and then opening it locally and so on. You take the code that you wrote that reads, for example, that radio astronomy data looking for the evidence of green bug-eyed monsters, and you add a little bit of extra stuff, not very much, a little bit of extra stuff. And the result of that is now you can run that code as a screensaver, and you can make that screensaver available to millions of people around the world who have idle desktop PCs that they could put to work in the search for green bug-eyed monsters out in space or whatever. Okay, don't get too scared. So yesterday, I checked this yesterday on their webpage. Yesterday, there were 169,000 volunteer people who had put that screensaver on their laptop. This is for all, I think this was for all the different projects, not just for SETI at Home, but for all the different BOINC projects. So almost 1 million PCs, and the 24-hour average for how much computing capacity was devoted to those projects was 10 quadrillion calculations per second on average for 24 hours. So you can multiply that up to figure out the total amount of compute capacity available over all that time. If that were a single supercomputer, it would be the 11th fastest supercomputer in the world. Now, the other 10 in the list of fastest supercomputers in the world, again, top500.org, for those of you who want to look this stuff up, the other 10 supercomputers, each one of them cost at least tens of millions of dollars, perhaps hundreds of millions of dollars. But this collection of volunteer PCs costs literally nothing. Now, of course, I just lied. It cost the owners of the PCs whatever they paid, but they paid that anyway. Now, they did pay a little marginal amount into doing this, which is they had to pay for the electricity. They had to pay for the power to run the PC when it was being used to look for extraterrestrials or try and cure human diseases or whatever project they happen to be running. It didn't cost the projects any money, and it cost the volunteers who provided their PCs only a very little amount of money, not very much. I will tell you, if this were a PC at somebody's home, I know that nothing we run in my house produces a measurable amount of power consumption except the air conditioner. Literally, you can tell the difference between the summer months and the winter months just by looking at the little graph on the power bill. Oh, look, here's June, July, August, and September. And then the rest of the year, my power bill is a fixed dollar amount that is basically just taxes, right? I'm exaggerating a little, but to first order, that's true. So if I had a desktop PC, I could run SETI at Home or whatever, and it would not have a measurable effect. Whereas, if I had 1,000 PCs, that might add up to a significant amount of money. But for an individual PC at home, it's not a big deal. Okay, and then a note to self, and this was a great trick that someone I knew in grad school used to do, because they had science that was very hard to sell as it was going to save lives and property, right? You can easily sell, oh, we need money for weather forecasting because people get hit by tornadoes and die. Or you can easily sell, oh, we need money to cure diseases because, people get sick and die, right? So it's trivial to sell those things. It's much harder to sell things like extraterrestrial intelligence because nobody, well, let's say that it's very difficult to predict whether that's going to be a win or a loss. So nobody in Congress wants to pay for it, right? But this way, if you're doing amazing computing, then you might be able to get a little money for that, even if you can't get money for the science that no one wants to fund. Okay, now, Condor. Condor is a different technology. It comes to us from the University of Wisconsin-Madison, particularly Maron Livny's group. And Condor is a lot like BOINC and also somewhat different from BOINC. So Condor, it's opportunistic. It steals computing time from idle PCs. It runs in background and it waits. So it's always running on your PC, but it's biding its time until you're not using your PC for anything. Again, meaning low CPU utilization, nobody touching the keyboard, nobody touching the mouse, right? And it lets you get a lot more value out of the PCs that you've already purchased because that's, again, a sunk cost. You might as well get more out of it. The big difference between HT Condor, HT being short for high throughput, it used to just be called Condor. I suspect there was something else called Condor that made them change their name. But HT Condor, you don't have to add anything at all to your software. You have to make sure your software is not doing a few funky things, but you don't have to add anything into your software. You don't, unlike BOINC, and I'll roll back for a second. So in BOINC, you have to put in a little bit of stuff. You have to change your code a little bit. Unlike BOINC, you don't have to make any changes to your code at all. Condor works really well under any Unix-like operating system, or at least most of them. Significantly less well under Windows. I'll talk about that in a moment. And then Mac OS is kind of a weird middle ground because Mac OS is built on top of a version of Unix. But I was reading the manual for the most recent stable version, and it said, well, the way we're doing it now on Mac OS is fairly new, and it's not really as well debugged as we will be eventually, but we're not there yet, so be patient with us. Is rough. I'm paraphrasing, of course, but that's roughly what they said. Okay, so and it's one of the difficulties I think that makes HT Condor a little less attractive to individuals compared to BOINC. Is that it's not as trivial to install on your PC and as like SETI at home would be. Okay, so it's opportunistic, doesn't require any change in the software, and this is a really wonderful feature of HT Condor. I suppose this is sort of true in the case of SETI at home as well, but not really and not in the same way, I don't think. But HT Condor, in the version that runs on Linux and other Unix-like operating systems, it can automatically checkpoint. So to checkpoint means to write to disk the values of all of the variables at a particular moment in the run. And the reason this is wonderfully valuable as a capability is because you might be doing your thing, your number crunching might be running on my PC, and then I come by and touch the keyboard, and now your stuff has to shut down. Now, one way that your stuff could shut down would be simply to literally suspend itself, just to pause in the middle of the run and sit quietly until I go away, which surely eventually I will go away, right? So just wait patiently and sit quietly. But the wonderful thing about Condor is that Condor jobs, or at least certain kinds of Condor jobs, don't have to do that. They can instead shut themselves down when you touch the keyboard and then go to another PC that in the meantime has become idle. So they can migrate to somewhere else, which means they don't have to stop running. They just pause, move, and start up again from where they left off. And that's a wonderful improvement over just waiting patiently until you go away, because you might not go away for 12 hours. I can't speak for anybody else in the room, let alone out in TV land, but when I sit down with my laptop, I ain't going anywhere for quite a while. I might be up till 3 in the morning, right? I don't like to do that, but sometimes that's what it takes. So you might not get a lot of value out of my PC, but if there's another PC that you'd be very happy, your job would be very happy over there. So I mentioned it, so it can preempt the jobs that are running. And oftentimes the way this will be set up is if someone touches the keyboard or the mouse, the job will pause. And then if it's paused for too long, and this is something that can be tuned by the user, if it's paused for too long, then the job can go migrate to somewhere else, right? So if you're only on the PC for 5 minutes, then it might as well not try and go anywhere because that's going to take 5 minutes. But if you're going to be on the PC for 5 hours, then after it notices you're going to be there for a while, then it can go somewhere else. Right? Okay. And the other fun thing is that, and this is true of BOINC as well, all of the I/O can be done over the network to disk space that's owned by the person whose number crunching is running through HT Condor instead of running natively on the disk of the PC that you own. Because after all, you may not be volunteering a lot of disk space, if any, to that job. You may just be volunteering your CPU and RAM, right, when you're not using them. So it can do all of the I/O over the network. Obviously, of course, that I/O is going to be slower than local I/O would be. But the advantage is it doesn't take up the local space. And if you're not doing a lot of I/O, if you're just doing a little bit of I/O, then that doesn't bother you because a little bit of something slow is not going to make the whole thing all that much slower. Okay. Plus, it's free. So once upon a time, we actually did do this at OU. We had to stop, but we didn't stop because of the technology. We had to stop because at the time we were having a lot of turnover. We were doing this in the PC labs, some of the PC labs on campus. And we had, I think it was almost 800 PCs that were running HT Condor jobs. And it turned out that they were idle about 80% of the time. I mean, if you think of a PC lab, right? So during the day, on a weekday, when school is in session, it's probably busy. There's probably people in the lab taking a course or whatever. But that's, 8 or 9 hours a day, right? 8:30 until 5:30 or something, right? There's a few night classes, but not that many. And then, so you don't have nights and you don't have weekends and you don't have holidays and you don't have intersession and you may not have nearly as much uptake during the summer. So we found that 80% of the time, these PCs could get used to do number crunching, which was great. So we were getting 5 times more value out of, again, a sunk cost. We were buying these PCs anyway. But the difficulty we found, and eventually we had to stop doing it, was that there was a lot of turnover in the team that was running the labs. And the reason there's turnover is, of course, IT professionals, as soon as they learn an exciting new skill, they can go get an industry job for twice as much money, right? So there was a significant amount of turnover in the team, and it became impractical to constantly be reteaching the lab team, who were always overburdened because they always had job ads. They didn't have enough people. They were always overworked. It became very hard for them to keep up with that. And so we finally realized that it was only contributing about 15, 20% of additional compute capacity to what we were doing. And we thought, can't really justify the cost to them in labor and inconvenience for us. However, if you've got a stable lab team, you may be able to do this, and it worked really well. We were able to get it to go pretty well. But so it's wonderful. So you've got a lot of extra capacity. It's unused. You can get a lot of bang for your buck. That 80% may be a little bit of an underestimate. Some days it was like 90, 95%, depended on when. A few things, a few limitations. If you can't run it on a native Unix or Linux machine, it becomes more problematic because the version that runs under particularly Windows, unfortunately, they call it clipped. They have a lot of bird metaphors in the HT Condor world. They refer to the Windows version as the clipped version. It cannot do the checkpointing and it cannot do the migration. So if someone touches the keyboard and the mouse on a Windows machine running Condor, HT Condor jobs, then those jobs can pause, but they can't go anywhere. They have to sit and hope. And in particular, if somebody powers down that PC, then whatever that thing was working on is gone because it didn't have an opportunity to checkpoint itself. Okay. You want to not run codes that are parallel in the sense of the parallelism is built into the code. So you don't want to run like an OpenMP job. You can, but we're going to keep away from that. You don't want to run an MPI job to do the opportunistic version. Now you can run MPI jobs under Condor, but that's not the same kind of circumstance. It's not the opportunistic approach. You typically have to be able to compile your code with a very specific set of compilers. Typically, you can only use, on most systems, you can only use the GNU compilers. You can't use like a third-party commercial compiler typically. Because although you don't have to rewrite your code, you do have to recompile your code. Well, even that's a slight oversimplification, but we'll leave it at that, okay? And then you might have other limitations depending on what PCs are available. So for example, you need to know how much RAM your job is going to need, because if you've got two PCs that are sitting idle and one of them has 32 gigabytes of RAM and the other has 1 gigabyte of RAM and your job needs 2 gigabytes of RAM, you better not go to the one that only has 1 gigabyte of RAM. So you have to have some reasonable guesstimate of how much RAM your job is going to need. Likewise, you know, if it's going to have some internal parallelism or whatever, you need to know how many cores it's going to need, whatever resources your job is going to need. Okay. Other than that, running an HT Condor job is an awful lot like running a batch job on a traditional tightly coupled HPC cluster supercomputer, right? So you write a batch script and you submit it using some batch script submit command, and it magically goes somewhere and runs at some point, which you don't know when and where. Eventually, you'll get an email saying it's done. Okay. So here's actually a script, a batch script that I used on some tests a few years ago. I hope it's not out of date, but my guess is it's pretty much still up to date. I'm not going to go into what universes are, but there's different ways to run Condor jobs, yada, yada, yada. But there's my executable, and that's on the machine that I'm submitting from. It's going to copy my executable to any machine it'll run on. So it needs to know where it is on the submitting machine. Under what circumstances should it send me an email? So I only want it to send me an email if it fails. There's the email address to send it to. If it's got some command line arguments that it takes, those are listed there. And then, of course, standard input, standard output, standard error files, right? And it'll, and a log file that'll tell me what happened. And then the directory that I'm going to start the run in, and then this Q thing means go. And then I use this command condor submit, and it give it the batch script, and magic happens later, and I don't know when or where, but eventually I'll get some information back. Okay, how am I doing on time? Am I over or under?
No, it's 1:12.
Okay, I'm more or less where I should be. We might actually end a few minutes early, weirdly enough. Okay, let's talk about grid computing. Nobody knows what grid computing is, and everybody who thinks they know what grid computing is has a different definition from everybody else who thinks they know what grid computing is. That's also true of cloud computing, which could be the same thing or different, and nobody knows, and nobody can agree on what they are. How's that for a starting? Okay. Nobody has the faintest idea what these terms mean, except that everybody has a different idea what these terms mean, and nobody can come to a consensus, and that's okay, and we don't care. Okay, so given that nobody can define it, this is the best definition I've ever heard, and it comes courtesy of my sister, who I think heard it from others, but the only person I've ever heard this definition from is my own sister. And so I'm going to attribute it to her. So a distributed heterogeneous operating system, that's what a grid is. So you can have compute resources and storage resources, networks, collections of data. There's a zillion stuff, right? You can have sensor networks on there, and things that produce data, things that consume data, things that hold data, things that produce number crunching, and so on and so forth, right? There's lots and lots of stuff that can be in there. I'm going to leave out the part about the human beings. I'm not sure I believe that the human beings are directly part of the grid. There's human beings who provide grids. There's human beings that use grids. I don't think they're really part of the grid as such, but others may disagree. Okay. So here are many sad attempts. This originally came off an IBM website, but the web page that it was originally on the IBM disappeared. And it's not on the IBM website anymore, at least the last time I checked. But then somebody else found a copy of it, and then they put it on their website. So the quotes are still there. But on the other hand, it's not the original people who currently make the quotes available on the web. But you can go to that web page and find that stuff about, what is grid computing. It used to be an IBM web page. So Grid computing keeps complexity hidden. That's good. Mainly enables, unlike the web, which mainly enables communication, grid computing enables all kinds of stuff. It's like peer-to-peer in using shared files, but it's unlike peer-to-peer in having many-to-many sharing, which actually now I think peer-to-peer includes many-to-many. So that, among other things, that quote's out of date. It's like clusters and distributed computing in the sense of bringing computing resources together, but it's unlike them because they don't have to be near each other, right? And they don't have to be similar to one another. It's like virtualization technology, but it's unlike virtual, right? So if the way you define something is only by comparing it to other things, you already know you don't know what it is. But that's okay. As they say about art, I don't know how to define it, but I know it when I see it, right? Okay, so Condor is a kind of grid computing. It has the various qualities that people usually talk about when they talk about grid computing. So you create a grid out of these volunteer, typically these are desktop PCs, although they don't have to be, right? You can run Condor, HT Condor on well, you can run it as your scheduler if you have a cluster supercomputer, or you could run it on a giant pile of servers or whatever you want. And I can't remember what year it was, but several years ago, I think it was Red Hat incorporated HT Condor into at least some of their releases. So it's now sort of built into the operating system, but sort of not. It's all very fuzzy, and if it sounds complicated, then I've explained it correctly. If you're confused, I explained it right. Okay, all right. But all of that is invisible to you as a user. You just write your little Condor script, and you submit it using Condor submit, and magic happens. That's all you need to know, right? Okay, now cloud computing. Again, nobody can tell us what cloud computing is, but it sure sounds good. And it actually has been unbelievably successful. And I've got some numbers about that. In fact, the only intelligent things I can talk about with cloud computing is commercial cloud computing and how it's a huge business, which proves that it's a real thing because people wouldn't be paying that much money for it if it was completely useless. Okay? They might pay a little money for it if it was useless because they just want to see what's going on, but not the big money. So just tootling around on the web last night was where I found this stuff. So this diagram came from an article on some website, and it's the market share for various cloud, commercial cloud carriers in calendar 2000, or I guess it was the fourth quarter of 2017. So Amazon is way out in front with about a third of the market. Microsoft is number 2 with a little more than a third of what Amazon has. And then I didn't realize IBM was number 3 and Google was number 4. But then Alibaba, which is the big retail website in Asia, is a big cloud computing company now. And then there's 10 more that are, a bid, and then the entire rest of the market is 20%, right? So, and, things are going up and down a little bit. I mean, but, not by huge amounts. So it's, there's a pretty good array of these, but it is it's an enormous, gigantic business. So Amazon Web Services was almost $17.5 billion in calendar 2017. That's an amazing enough number, but we don't really have a good sense of what that means. What we do know is how much it grew from the previous year. It grew 43%. It grew almost, so that's Moore's law growth level. That is doubling every 2 years, right? Because the square root of 2 is 1.414. So this is slightly faster than doubling every 2 years, right? That's just amazing. But the really amazing thing was that the web services accounted for almost 3/4 of Amazon's net income during that quarter, during the last quarter of 2017. That's unreal. And by the way, the last quarter of 2017 is the biggest retail quarter of any year, the fourth quarter. That's when people are buying Christmas presents, right? And during the quarter when people were buying Christmas presents, right? Amazon is a retail company that has a cloud computing service as an add-on, right? No, not anymore, right? Now Amazon is a cloud computing company that has a retail service as an add-on. Now I'm sure Amazon would not characterize themselves in either way, but in terms of the contribution of what was originally, hey, you know, we've got all of these idle PCs that are there to pick up the slack during the Christmas season when people are doing a lot more ordering, right? So Cyber Monday is when there's supposed to be like the most orders for online retail, which is during the fourth quarter. Well, apparently during the fourth quarter, that thing that was originally, oh, you know, the rest of the year these PCs are idle, we might as well get some use out of them. Now, that's core to the business and it's the bulk of their profits. Microsoft, Azure doubled in one calendar year, right? Their cloud service doubled in a single calendar year compared to Windows revenue grew by 4% during the same period, right? So this is a game changer for all of these companies. It's changing how they can make money and how much money they can make. IBM, they were up a mere 24% in calendar 2017, but in the fourth quarter, they were up 30%. So that's not quite Moore's Law, but that's sort of headed in the direction of Moore's Law. So even though they're sort of, you know, jockeying for position, yeah, I'm almost done. Even though they're sort of jockeying for position in terms of market share, the growth for all of them is unreal. It's amazing how much growth they're having in this business. It's fundamentally changed how everybody does their computing. All right, and that's actually it. So we're done. I think this is the only time we'll end early, ever. So we'll be back next week to do GPU stuff. And we'll look forward to seeing you all then. Are there any questions in TV land? Okay, thank you everybody, and we'll talk to you next week.